Okay, so in this video we want to continue on from where we left off in the last video, which was beginning to talk about the idea of standardizing a non-standard normal distribution back to the standard normal distribution. So that is the distribution where the mean is 0 and the standard deviation is 1. We do want to continue to talk about that today. We also want to have a look at something called the 68, 95, 99.7% rule. Now those of you that might study further maths as well as math methods will be familiar with this rule and have a sense of what this is about. But this is actually a nice point for you because actually in methods we have the tools to be able to understand where those numbers actually come from. Okay, so let's have a chat about that now. So let's have a think about remembering that a normal distribution is an example of a continuous random variable. We have a function that describes the curve. I've got that defined in my CAS over here already. And we know that if we wanted to find probabilities, we're looking at area underneath the curve. Okay, so that's the key thing we want to understand about continuous random variables. So if the question is, what percentage of values of a normally distributed variable lie within one standard deviation of the mean? Okay, so if we've got our standard normal distribution here with its mean at 0 and one standard deviation, within one standard deviation of the mean means between +1 and -1. Okay, so what we're calculating here is we are calculating the probability that z is between -1 and 1. Okay, and we're going to do that using an integral. So we want to find that how much area is underneath the curve between -1 and 1. So if we integrate this, I've got the function already defined here, from -1 to 1, and obviously it's a symmetric function, so you could also do 2 times the integral from 0 to 1 if you prefer, but we're not going to do it by hand anyway, so if the CAS is going to do it for us, it doesn't make much difference. And when we do that, we find that we've got 0.6827, let's say. So probability, we're quite often asked to give our answers correct to 4 decimal places. 0.6827, okay, which means that that's approximately 68% to the nearest percent of the distribution. So under the standard normal distribution, approximately 68% of the distribution lies within one standard deviation of the mean. Now that would then apply to other distributions because the curve is still the same, we're just transforming and translating it. So if I had a different distribution, we've talked about IQ before now, where the mean was 100, and the standard deviation was 15, which would make this 100 plus 15, 115, and 100 minus 15, 85, okay, we would find that for for the variable IQ, which has mean of 100, which is normally distributed with mean of 100, standard deviation of 15, that what the interpretation of this would be that approximately 68% of the population should have IQs between 85 and 115. The other thing that this allows us to do is use the symmetry of the curve. So we would also be able to work out, well, what probability must be up here? Okay, so if this is 68, what proportion, sorry, must be up here. If this is 68% in here, well, that means that there's 32% that aren't accounted for. And it's a symmetric shape. So that means there must be 16% up here, and there must be 16% down here. So we get all sorts of facts by knowing this. Now to be clear, and this is what you don't learn, those of you who know this from further maths, is it's not exactly 68%. We can see that it's actually 68.26894921, etc. %. Okay, so it's approximately 68%, but it does allow us to give some context for standard deviation. What does it actually tell me if I know that I've got a standard deviation of 10? You know, in the context of this variable, okay, that tells me that about 68% of the distribution is within 10 of the mean. Okay, that's useful. All right, let's think about within 2 standard deviations of the mean, and perhaps you've already cottoned on given the name of this section. So what we're calculating here is the probability that the standard random variable is between -2 and 2, so that is within within 2 standard deviations of the mean of 0. So if I adjust my calculation here and integrate my probability density function from -2 to 2, we find that this is approximately equal to 0.9545. Okay, so to the nearest percent, that is about 95%. So approximately 95% of the distribution is within 2 standard deviations of the mean. Now there are a couple of questions in an earlier binomial exercise that I accidentally set for you to do, which sort of reference this idea. And there is a sense that in any distribution, whether it's a normal distribution or not, if the distribution's roughly symmetric, then we can often say that within roughly 95% of the distribution will lie within 2 standard deviations of the mean. And there was a question that did require that interpretation earlier that I shouldn't have set for you at that point, but that might make a bit more sense at this point. And then finally, so again, if we think about our example of our IQ, 100 plus 2 standard deviations of 15 would be 130. 100 minus 2 standard deviations of 15 would be 70. So we're saying that roughly 95% of people would have an IQ somewhere between 70 and 130. Okay, that would be the interpretation. And then let's think about within 3 standard deviations of the mean, probability that Z is between -3 and 3. Again, it could be less than or equal to. It's no different for a continuous random variable. So working out this integral, adjusting this calculation in my CAS, integrating from -3 to 3, the standard normal PDF, and we find that that's approximately 99 point, no, sorry, write it down the decimal first, 0.9973. Now, the other two values we rounded to the nearest percent. The problem we would have here is if we rounded to the nearest percent, we'd be saying 100% of the distribution lies between within 3 standard deviations of the mean. And it's never going to be 100%. The PDF goes on and on forever to infinity, and so we can't actually write that, and so therefore we approximate this value to 1 decimal place, which is going to be 99.7% of the distribution is within 3 standard deviations of the mean. So you might remember I said to you previously that when you draw the standard normal curve, you should be seeing pretty much all of the distribution happening within 3 standard deviations of the mean. So if you're going to sort of scale an axis, you want to put whatever 3 standard deviations of the mean is. So again, if it's an IQ, 100 plus 3 lots of 15, 145 should be sort of right towards the end where you're looking like having very little area left out here. Okay. So again, if we think about that and taking away 45 from 100, that would be 55. So the interpretation here in the context of that standard normal variable, of the IQ variable, is that approximately 99.7% of the population should have an IQ between 55 and 145. And again, like I looked at in the first example, in the first 1 standard deviation from the mean situation, that we can still use symmetry. So if we've got 99.7% of the population in here, it means there's 0.3% of the population that are unaccounted for. So that means it is 0.15% going to be bigger than have an IQ higher than 145, and 0.15% have an IQ lower than 55. Okay, so all those sorts of interpretations and symmetries we can use. I would strongly encourage you when you're solving problems involving the normal distribution to draw yourself the bell curve and have a look at the areas that you're referring to. Okay. This is known as the 68, 95, 99.7% rule. It's not the most catchy name. Pretty much gives itself away in its title. And that says that for any normally distributed variable, approximately 68% of values lie within 1 standard deviation of the mean, 95% of values within 2 standard deviations of the mean, and 99.7% of values within 3 standard deviations of the mean. Again, being clear about this isn't perfectly precise. They're approximations. Okay. Alright, so example 1, scores obtained on an IQ test. So we've been using this example as we've worked through, so we've got these numbers to hand, are normally distributed with a mean of 100 and a standard deviation of 15. So that tells us that approximately 68% of the scores will lie within 1 standard deviation of the mean. So mean minus 1 standard deviation is 85, mean plus 1 standard deviation is 115. Okay. Approximately 95% of the scores will lie within 2 standard deviations of the mean. So mean minus 2 standard deviations, 100 minus 2 lots of 15 is 70, 100 plus 2 lots of 15 is 130. And then approximately 99.7% of the scores will lie between, so we know within 3 standard deviations of the mean, so 100 minus 3 lots of 15 is 55, and 100 plus 3 lots of 15 is 145. Okay, so then we want to think outside of that. So what percentage of scores is above 115? Okay, so let's have a think about what's happening here. So we've got our normal distribution. If I was answering this question from scratch, I'd be drawing up a bell curve with the mean at 100, with my 3 roughly spaced standard deviations taking me pretty much to the end. This would be 115, 130, 145. This would be 85, 70, 55. So we want to know what percentage of scores is above 115. Okay, so we're interested in this bit of area up here. Now, what we know is that within here to here is 68%, we also know that the total area is 100%. So therefore, we've got 32% outside of that red area, which means that if we're given that it's a symmetric curve, this should be half of 32%. So 16% up here, and that the logic then would follow that it's 16% down here. Okay? So the probability that someone has an IQ score bigger than 115, now remember it doesn't matter whether it's bigger than or equal to or bigger than, it's a continuous random variable, is, so it says what percentage, normally I'd give a probability as a decimal, 0.16, but what percentage, we know it's not exact, but it's approximately 16%. What percentage of scores is below 130? Okay, so we want to think about, you want to sort of be able to work out, first of all, 130 is how many standard deviations away from the mean. Okay, so 130 is 2 standard deviations above the mean. So we want to know what percentage of scores is below 130. Okay, so the total area. Now, 2 standard deviations from the mean, we know that's to do with 95%. So we know that within here, within the middle, we know this is 95 in here. So we also, though, want to include this bit down here, okay, in our, if we want probability of the score being less than 130. So again, we want to use that symmetry idea. Okay, there's 95% in the middle. That means there's 5% unaccounted for that must be equally balanced either side. So that's going to mean 2.5% up here and 2.5% down here. And so therefore, the probability that an IQ is less than 130 is going to be approximately, so we've got the 95% in the middle there, plus the additional 2.5% that we need to add on at the end. So it's going to be about 97.5%. What percentage of scores is less than 70? Okay, so let's think about this here. Less than 70. So again, 70 is about 2 standard deviations, so we're going to want to use the 95%. Okay, so again, we know 95% between 70 and 130. Okay, so that's what we want to use, but we want to know what proportion are below 70. We actually already worked that out up here. That is 2.5%. So probability that someone has an IQ that is less than 70 is approximately 2.5%. I'm really hoping you can't hear that, but someone's just started a leaf blower outside. Hopefully that's not being projected through the microphone. Okay, part E, what percentage of scores is between 85 and 145? Okay, so this is a slightly different one. Again, draw a diagram, see what you're dealing with, be clear about what's happening, okay? So our mean's 100 still. So 85 we know is 1 standard deviation below the mean. 145 is 3 standard deviations above the mean. So we want to work out, okay, what's the area between 85 and 145. So what we want to think about is that we know that 85 to 115 is 68%. So therefore, again, it's all about symmetry. 85 up to the mean, that bit there must be half of 68%. So that has to be 34%. And again, same sort of idea. We know that within 3 standard deviations of the mean, either side of the mean is 99.7%. So this must be half of 99.7%. Okay, so that's going to be, what's that going to be? 99.7 divided by 2. Sorry, I know I should be able to do that. The leaf blower's throwing me. 49.85%. Okay, and so therefore, the probability that an IQ score is between 85 and 145 is going to be approximately 34% plus 49.85%, which is half of 99.7. So if I add 34 onto this, it's going to be approximately 83.85%. Okay, so using various symmetries to calculate what you're after. Okay, so let's again recall this idea of standardization and this idea of, you know, any area underneath the a non-standard normal distribution can be corresponded back to an area under the standard normal distribution. So you might remember we talked about, okay, well, if I'm going to draw it slightly differently than how I did it before, but it's the same idea. If I want to know what's the probability that x is less than a, that's that area there. Okay, I'll draw it as less than or equal to a. And then that's going to correspond to an area under the standard normal distribution. Okay, and remember the transformations that are going to happen here is we need to translate to the left by the mean to take the mean from mu back to 0. So we're going to take our a value and subtract the mean from it. And then we also need to divide by the standard deviation to squash the standard deviation from being sigma here to being only 1 down here. Okay. So therefore, this is the same as the probability that z is less than or equal to a minus the mean divided by sigma. So we've already had this information in the previous page in your booklet. So this idea of standardization. So a, sometimes you'll see that written as x. Doesn't matter. It's an x value in the x distribution, and then we take that x value, we subtract the mean and divide by the standard deviation to get that back to a standard distribution. As I said, standardization is important when we are trying to compare things. And the other thing is that it gives you an interpretation. So we talk about a Z-score. Okay, so what we're calculating here, when we calculate a minus the mean divided by the standard deviation, we're calculating what we call a Z-score. Okay, and what that does is that tells us roughly how many standard deviations above or below the mean are we. So it looks like here I'm going to get a Z-score that's maybe, I don't know, let's approximate, let's say that's about 0.4. And so if I know that the Z-score for A is 0.4, that is its equivalent value in the standard normal distribution is 0.4, what that tells me is that A is about 0.4 of a standard deviation above the mean. If I got a Z-score that was negative, that would tell me my value is actually below the mean. And obviously it gives you a sense of how far away from the mean it is. So, as it says over this next page, if x is a normally distributed variable with a mean of mu and a standard deviation of sigma, then any value x in the distribution can be converted to a value z in the standard normal distribution using this formula. You take the x value, you subtract the mean, you divide by the standard deviation to get the z-score. Standardization is useful in making comparisons between distributions, and we'll have a look at that in an example. But it also gives us a direct comparison to the standard deviation. So for example, if you got a z-score of negative 1.5, it means that that value is 1.5 standard deviations below the mean in its distribution. Okay. So as we know, let's go back to our familiar example of IQ scores. They're normally distributed with a mean of 100 and a standard deviation of 15. Find the standardized value of an IQ score of 90. So sometimes we would call this the Z-score. Certainly in further maths we refer to it as a Z-score quite frequently. So the standardized value, the Z value or the Z-score, is going to be the actual value, the X value, minus the mean of X, which is in this case is 100, and divided by the standard deviation of X, in this case that's 15. So this is negative 10 on 15, okay, which is going to be negative, what am I doing there? Dividing by 5, so negative 2/3, okay? And so therefore, what that tells us is that an IQ score of 90 is 2/3 of a standard deviation below the mean IQ score. Okay, so it tells us how many standard deviations away from the mean are we. Okay, so this means IQ score of 90 is 2/3 of a standard deviation below the mean IQ score. So, you know, you can then use that tells you you're in the bottom 50%. Okay, you can also use your, but you're not more than one standard deviation away from the mean. So you're also in the middle 68%. Okay, you could think about, you could work out one standard deviation below the mean. We know there's 16% of the distribution less than that. So that means that you are higher than the 16th percentile, or you are in the top 84% of the distribution. Okay, so lots of ways that you can interpret that given the information we've talked about in this lesson. As I said, the other reason we might want to standardize would be to make comparisons across two distributions. So let's say, for example, two maths classes sit two different tests on the same topic. The results in class A are normally distributed with a mean of 72% and a standard deviation of 8%. The results in class B are normally distributed with a mean of 68% and a standard deviation of 10%. Brady is in Class A and he scored 74% on his test. Jeremy is in Class B and he also scored 74% on his test. But who performed better relative to the test they were doing? Okay, so obviously we can see that, you know, Jeremy's result is certainly a lot higher than the mean, than Brady's, but equally they've got different standard deviations as well. So what does that actually mean in terms of roughly where do they sit in the ranking of their classes? Okay, so we want to work out the Z scores for each of them. Okay, so for Brady, he's in Class A. He's in Class A, scored 74% on his test. So his Z score is going to be his actual test score, 74, minus the mean of his test, which was 72, over the standard deviation of his test, which is 8. Okay, so that's going to be 2 on 8, so that's going to be 0.25. So he scored 0.25 of a standard deviation above the mean of his class. Jeremy, on the other hand, he's in Class B. His Z score, he also scored 74. The mean in his class, though, was 68, but there was also a higher standard deviation of 10. Okay, so this is going to be 6 on 10, which is 3/5, or 0.6. Okay, so Jeremy actually scored 0.6 of a standard deviation above the mean in his class, and so therefore his score is a higher Z score, and his score relative to his peers is a better score. Okay. So therefore, Jeremy performed better. Okay, so Z scores or standardization useful for A, getting a sense of how many standard deviations away from the mean is this score, and B, useful for comparing across two distributions. We also want to get familiar with the 68, 95 and 99.7% rule, thinking about the symmetries allowing us to approximate various probabilities that are either 1, 2 or 3 standard deviations above or below the mean. The work to practice this is in exercise 16b, questions 3 to 14.